under special cases, you can actually have a 2D growth where the nuclei has a surface energy such that the contact angle with the substrate is essentially 0. Another way to say it in layman's terms is the nuclei really likes to stick to the substrate. If the nuclei really likes to stick to the substrate, it may not want to do a 3D growth, but rather do a 2D growth. So, if you look into the figure, here is a nascent nuclei, and the nascent nuclei is subcritical. So, it will get it will coalesce with a larger nuclei, and supposing the larger nuclei is this blue region here, and these nascent nuclei, instead of sort of growing on top of each other, tend to stay on the substrate and diffuse to the edge of the larger nuclei and get coalesced, and what you end up forming is a very thin film, in extreme cases a one dimensional in the z direction. So, it is like a single monolayer of atoms. So, a single monolayer of atoms that is sort of growing laterally across your substrate. From an epitaxial point of view, this sort of mode is preferred because the 3D growth tends to have a lot of grain boundaries and a lot of other issues, and this does not. Thankfully, this is also the common occurrence when you are doing homoepitaxy, which is when you are trying to grow silicon on silicon. From a nomenclature standpoint, this is called Frank van der Merwe growth. The advantage is that even for very thin films, you will get 100% coverage. Or conversely, if you are trying to grow very thin films and you want 100% coverage, you should select conditions that propagate or promote 2D growth rather than 3D growth. Now, one thing that we should answer is what is the mechanism by which these grains are coalescing. So, thermodynamics tells us that there is a subcritical grain or a subcritical nuclei, and then there is a supercritical nuclei. The supercritical nuclei will grow, the subcritical nuclei will shrink. But what is the mechanism of this transport? Because unless we understand the mechanism of this transport, we can't say anything about the kinetics of this process. So, given infinite amount of time this process will happen, but how fast this process will happen can only be answered if we understand its kinetics. And while the details are always more complicated, in the simplest way you can imagine this process will occur through surface diffusion. Right. So, this is what I am trying to show here, that the way these subcritical nuclei are approaching this larger grain is through surface diffusion. Surface diffusion, as you all know, is temperature activated. So, D is proportional to some activation energy by kT. Typically, the activation energy of surface diffusion is around 25 to 50% smaller than the bulk activation. So, if you remember the diffusion lecture, we talked a lot about dopants, right, and we talked a lot about impurities, and we discussed how those impurities diffuse in bulk, and they had activation energies for substitutional diffusion or activation energy for interstitial diffusion. Surface diffusion tends to be around 25 to 50%, the activation energy tends to be 25 to 50% smaller, which means the surface diffusion is much faster than bulk diffusion that we have discussed till now. This is sort of important because bulk diffusion tends to be a relatively slow process and only happens at high temperatures. Because surface diffusion can happen at lower temperature, you can theoretically have high quality epitaxial growth at lower temperature, right? Otherwise, you will have to wait such a long time for your grain to grow that for all practical purposes it is useless. With that insight in mind, let us talk a little bit about what is the distance between two nuclei. So, till now what we have discussed, just to recap, is that nuclei will form. The nuclei will form if the supersaturation condition is achieved, and more the supersaturation, more the nuclei will form. But what is the average distance between the two nuclei? The average distance between the two nuclei will be, as you can imagine, a very strong function of grain size, right? Or rather, it will lead to a difference in grain size. So, the concentration of nuclei also depends upon the critical Gibbs free energy, which is delta G crit that you saw in the previous lecture, and this is the absolute concentration is given by this formula. Now, the thing to notice is delta G critical itself depends upon the supersaturation, right, but it depends on the square of the supersaturation, and this square is inside an exponent. So, you can imagine this is an e to the power minus 1 over x square type of dependence. So, this is a very sensitive dependence. Very small changes in supersaturation cause very large changes in critical concentration. Now, this is a concept I want you to remember, we will come back to it. But in general, as you increase the supersaturation, the delta G vapor to solid becomes more negative. As it becomes more negative, the number of nuclei that keep growing increase significantly. And I'm showing the same thing in this figure here. With that in mind, let's also talk about the kinetics a little bit. So now the kinetics of nucleation process are a little more complicated. I don't want to go into the details, but in a very simple model, you can argue for a rate of nucleation. So this is the rate at which the nuclei would form on the surface, right? The kinetics of it. And supposing you are forming R number of nuclei per volume per second, and that R is basically given by the concentration of critical nuclei divided by an average tau, which is the lifetime of the nuclei. So how long does the nuclei lasts before it coalesces into a larger one, right? So the average time. Now there will be a distribution, but here we are just looking at an average time. With that formula, we can actually plot the rate of nucleation as a function of temperature. So we are plotting it in the Arrhenius model. So this is 1 over T. So this is increasing 1 over T, which means this is decreasing temperature. So this is high temperature, which is the melting point, and as you go, you reduce your temperature. Now this is the direction of less supersaturation, this is the direction of more supersaturation. And what you see is you see a U-type curve for nucleation. So the nucleation initially is very small. Why is it very small? Because you are at equilibrium. So at equilibrium, you should theoretically form no nuclei. Now as you increase the supersaturation, you are now creating a thermodynamic force for the nucleation to occur. You are taking water and you are freezing it below melting point, right? So when you are freezing it, the water is still super cold, so it wants to nucleate. So you are creating that driving force. The more you freeze the water below its melting point, the more you are creating that thermodynamic driving force. So the nucleation rate increases. There's a higher probability for the nucleation to occur. At some point, however, it peaks and then it falls again, and this is because of the kinetic limitation. You see, nucleation must form by agglomerating subcritical nuclei, right? And then the nuclei sort of needs to grow, but that process requires movement of material, which again happens through diffusion. So there is a kinetic limit of how fast this can happen, and if you reduce the temperature too much, even though the driving force for forming the nuclei is very large, the kinetics or the speed at which the nuclei can form are so small that you don't really create a nuclei. So that's what leads to this U-shaped curve. This sort of an insight is important to tell you that nucleation rate peaks somewhere in the middle. It's not highest at the melting point, neither is it a monotonic decreasing function. It's a U-shaped curve function. All right, moving on. Now, what does that tell us about the CVD process? So if you now look at the wafer, and if you look at what will happen to the nuclei on the wafer versus temperature, these are the three cases you see. So at temperatures very close to the melting point, you will have very few nuclei. So the average distance between the two nuclei will be large. Somewhere where the nucleation rate is the highest, you will have the maximum density of nuclei, a lot of small nuclei all over the place, right? But if you reduce the temperature even further, then at some point you will again have very few nuclei with the average distance very far off. Now, end of the day, this thermodynamics tells us that some nuclei will increase in size, some nuclei will decrease in size, and it depends upon their radius, right? So supposing this is the case where you have a large nuclei and this nuclei is above the critical radius, so it will grow in size at the expense of the smaller nuclei that are getting consumed. And this process is happening through surface diffusion, as we have just discussed. But diffusion has a temperature component, right? It will be a certain speed at which the nuclei will grow, and that speed will be decided, or rather that rate will be decided by how fast the material can actually transport from the small nuclei to the large nuclei. And this, since diffusion is such a strong has such a strong dependence on temperature, you can expect a curve like this, where the growth rate for the supercritical nuclei versus temperature looks like this. Once again, this is an Arrhenius plot, so the temperature is decreasing as I'm going towards the right. This is 1 over T. This represents the melting point. Because this is at higher temperature and this is at lower temperature, you expect the diffusion to be higher here than here, right? And because the diffusion is higher here, the growth rate is also higher here. Now, the consequence of this process on the wafer is also very apparent when you look at this. So, at high temperature you are able to diffuse, so your nuclei will grow in size, the growth rate of the nuclei will be large. At small temperatures, even though you have nuclei, they are unable to push the material to one nuclei, so you are not really growing them at any appreciable rate, that is why the growth rate falls. Okay. Now, we have seen the curve of the rate of nuclei, or rather the seen the curve of rate of nucleation, and we have seen the curve of growth rate. Now, if you put these two together, you finally understand the most important concept behind CVD, which is at what temperature should you grow things. So, you have seen this curve, the nucleation rate is a U-shaped curve. You have seen this curve, which is a growth rate, which is a monotonically decreasing function as temperature decreases. You can ideally do the growth here, right, which is very close to the melting point. This is the metastable region. The practical equivalent of this is the super cooled liquid, right. So, if you take a water bottle and you keep it in the freezer, there is a possibility that it will go below the melting point without actually freezing. At that point, the bottle is metastable. In fact, if you take that bottle and just bang it on the counter, suddenly you will see the ice form. So, that is because that water is sitting at a metastable state. It wants to nucleate, it wants to freeze, but it has not yet found a nuclei. Why? Because the nucleation rate is 0. You see, the nucleation rate has fallen. Now, because the nucleation rate has 0, the water has not started to freeze. And if the water has not started to freeze, even though there is a thermodynamic imperative for it to freeze, it is still waiting. So, that is the challenge. You see, thermodynamics predicts things that will happen given infinite time, but if you do not have infinite time, while you are waiting for that infinite time, kinetics tells you how fast that process will occur. So, in practical systems, by just playing with this equilibrium, what must happen at equilibrium and what must happen in by playing with the thermodynamic and kinetically controlled products, you can actually get different materials. Anyways, coming back to this. So, this is metastable region. Here you are not nucleating even though your growth rate is very large. So, practically speaking, this is not very useful for CVD. Now, as you reduce the temperature a little bit from the melting point, you get into a case where you both have nucleation and an appreciable growth rate. A lot of the CVD happens here because you have both growth and nucleation. So, you nucleate your you form your film and the film starts to grow. So, both things happen at the same time. And if you reduce the temperature too much, then you are in the regime where you nucleate a lot, but those nuclei do not grow, and if they do not grow, you do not get a full film, you just get droplets or you just get islands. Right? So, this is not useful for CVD because often we want smooth films. This is useful if you are doing quantum dots or something like that, but this may not be useful for thin films. As you increase the temperature, you get to the case where you do both nucleation but also grow films. And if you try to do growth here then and wait for a very long time, then it is a possibility that you would get a very thick film, a film with a larger grain size, but the growth rate will be very slow. Like the growth rate might be very slow. A lot of people sometimes that is why do a two-step CVD process, where they first start with a low temperature process where they do all the nucleation, and that the rate of nucleation and the average distance between the two nuclei then sets up their grain size, and then transition to a higher temperature, so they can then also get the higher growth rate, so they do not have to wait for a very long time to get a certain thickness. So, yeah, that is essentially the optimization between nucleation rate and growth rate. Now, this also has a consequence on epitaxy. So, supposing you are doing growth, right? Now, you can be in two cases, and these two cases are given in this figure. You can be in the case where the growth rate is higher or the temperature is too low, right? And in this case, what is happening is that the nucleation rate is relatively high, right? So, by the way, this high growth rate, I mean you are transporting a lot, you have a very high partial pressure. So, you are transporting a lot of material onto the surface. So, a lot of material is, the material flux onto the surface is very large. This is not the growth rate of each nuclei, right? So, this is different from the growth rate that we were just talking about. Right now, this growth rate is at the speed at which the film grows. So, supposing this film grows at very high growth rate, or you are doing this at very low temperature, in that case your nucleation rate is very high, because how do you get high growth rate? Remember, you increase the partial pressure, and what does higher partial pressure do? Increase supersaturation. And what does higher supersaturation do? Cause more nucleation. So, in this case the nucleation rate is high, but the surface diffusion rate is low. Why? Because it is either low temperature or you are not giving enough time for the nuclei to diffuse, because remember the distance that they will travel is some version of under root d into t. So, even if d is sort of large, but the time given to it to transport is very short, then it does not have enough time to diffuse. So, in some case what is happening is you are piling up material so fast that the material does not have the time to reorganize itself on the surface. And if it does not reorganize itself on the surface, then it cannot do epitaxy, because the whole point of epitaxy is that the silicon underneath orients the nuclei that are on top. So, the nuclei that are growing on top have the same orientation as the underlying silicon, and as these nuclei grow, that orientation is maintained and you get an epitaxial oriented film on top. But in cases where the growth rate is very high, where the material is getting deposited at a very fast rate or the temperature is very low, that cannot happen. So, often in these cases the growth is amorphous of polycrystalline. You are just not giving enough time for the material to orient. While in cases where the growth is very low, which means that the material is coming very slowly, which probably means the partial pressure of the precursor is low, which means the supersaturation is low or the temperature is high, in these cases the nucleation rate tends to be very low, the surface diffusion tends to be very high. So, you have a lot of time before more material gets dumped in for the nuclei that are growing to actually come, coalesce, orient themselves, etc. In these cases the growth is often epitaxial or crystalline. What we just discussed is just seen in this figure. So, here is the growth rate, which is again the rate at which the film grows, right, over 1 over T. So, this is an Adherian's plot, this is lower temperature, this is higher temperature, and this line represents the separation between a region where you tend to grow polycrystalline silicon and the region where you tend to grow monocrystalline silicon. So, what is happening at lower temperatures and high growth rates, you do not give enough time for the film to orient itself. So, what do you get? You get polycrystalline silicon. At high temperatures and low growth rates, you can epitaxial growth and monocrystalline silicon, right. So, these sort of insights are important because tomorrow when you are trying to do epitaxy and you get something off, then you can appropriately tune the temperature, supersaturation, pressure, etc. So, let us just finally conclude and say what are the good conditions for epitaxy, right. So, the good conditions for epitaxy is higher temperatures. Typically higher temperatures will allow material to move better and will give you better epitaxy, or have lower supersaturation, which for CVD basically means lower partial pressure, right, and lower partial pressure for the same reason that no nucleation rate. So, your nuclei are very very sparse, and because they are very sparse, they have a lot of time to reorganize themselves as the material comes in and grow. However, conditions for good epitaxy are also the conditions for slow growth rate. So, often epitaxial growth is very excruciatingly slow. If you are just trying to deposit a polycrystalline material, you can get much higher growth rates. Okay. With that, we actually come to the end of the part on nucleation and growth. Let us have, to take stock of what we have discussed till now, we have discussed how flow affects growth in a CVD reactor. We have discussed how things diffuse through the boundary layer onto the surface. It adsorbs on the surface. It does some chemical reaction, and that chemical reaction then leads to some nucleation and growth. Now, we need to talk about desorption. So, there are some products are being formed when CVD is occurring, right. There are some side products, and those side products must now desorb again through through the boundary layer out into the gas stream and to get pumped out, right. On top of that, often these other components, for example hydrogen, might do their own side reaction onto the surface, and those side reaction might cause some products that must desorb, etc. So, let us talk a little bit about this desorption process. So, from a mathematical standpoint, desorption and adsorption are sort of similar, it is just the direction is different. Both cases you are sort of dealing with the boundary layer and you must desorb or adsorb across the boundary layer. So, the math is very similar. Usually this is not a bottleneck, and because all of these processes are happening in series, so the slowest step decides, ends up being the most important step and decides the growth rate, etc. And this is not a bottleneck, this is not the slowest step, so often it is ignored. However, there is a very, very important aspect of silicon epitaxy that you can only understand if you understand hydrogen desorption. So, let us have one slide on that. So what happens in silicon is, supposing you are okay, so what happens in silicon when you are using hydrides? So a lot of silicon epitaxy happens through hydrides. So silane, dichlorosilane, which has 2 hydrogen, silane, which has 4 hydrogen, or disilane. So disilane has 6 hydrogen. So a lot of hydrogen in these reducing type chemical reactions. And silicon has great affinity to hydrogen. Even during cleaning lecture, we discussed how hydrogen forms a monolayer when you dip it in hydrofluoric acid. And that H passivation is very strong, and the H passivation is very useful. The same H passivation happens here. So you are doing CVD. So you have this silicon on the surface, but that silicon is not unsatisfied. They are not dangling bonds on the surface. There is so much hydrogen in the atmosphere that hydrogen bonds with that silicon to form a silicon hydrogen bond at the interface. Now, if you were to add another silicon atom and make this layer a little thick, you first need to break the silicon hydrogen bond such that you can insert a silicon silicon bond. So for that, the hydrogen must desorb from the surface, and that requires a certain amount of energy, and often in silicon epitaxy that is the bottleneck, right? So most CVD desorption is not a bottleneck, so we don't talk about it, but in silicon epitaxy at moderate temperatures, hydrogen desorption is the bottleneck. And I can show you that with this very nice data that actually is from one of my seniors. I did PhD at Princeton, and he was my senior, so it's actually from his thesis. So supposing you look at something called open sites. So what are open sites? The open sites are silicon which are dangling bonds. So silicon that don't have an hydrogen on top. These open sites are where the growth can occur, because here a new silicon can be added. If there is a hydrogen already present, then the silicon already has a bond, so it will not like another silicon atom to come. So this open site fraction is important. And what these curves are telling you, what is the open site fraction as a function of temperature for different partial pressures. So at very high hydrogen partial pressure, you see that the open site fraction is much lower. Why? Because there is more hydrogen, so the hydrogen reacts with these silicon dangling bonds and passivates them, so there are no open sites. As you reduce this hydrogen partial pressure, the open sites increase, right? Because there is less hydrogen, so there is more concentration of these dangling bonds. And these more concentration of these dangling bonds or open sites then have an impact on the growth rate. So if you now look at growth rate as a function of silane partial pressure, you actually get this sort of curve, where initially you get higher growth rate, which is what you would expect from a simple CVD process. The higher the partial pressure, growth rate always depends on partial pressure, great. So this linear region is what you expect. But at some point, it becomes sublinear and then becomes self-limiting. Why is it becoming self-limiting? Because right now you are not waiting for more height, you are not starved of more silane. There is a lot of silane. The partial pressure of silane is very high. What you are starved of is open sites. There are no open sites. The hydrogen is bonding onto the substrate, and that hydrogen is preventing further reaction from occurring. So you are always waiting for that hydrogen to desorb from the surface before a silicon can come and attach. Now, first question you can ask is, where is hydrogen coming from? Well, if you go and look back at the reaction of how we form silicon from silane, you would see that we produce a lot of hydrogen. So that itself, silane itself is a source of hydrogen, right? And secondly, a lot of these reactions are done in an hydrogen atmosphere. So you're also flowing several liters per minute of hydrogen to dilute the silane, and that can also be a source of hydrogen. It is this hydrogen that actually you can also see the same effect if you look at the growth rate versus 1 over T for different precursors. So you have seen some version of this figure before when we were talking about growth rate and we were talking about mass limited flow and reaction limited, mass flow limited regime and reaction rate limited regimes. So these black curves you have already seen, right? So growth rate tends to show this 1 over sort of exponential dependence at low temperatures. However, if you were to do this growth not with hydrogen dilution but with nitrogen, so let's take the black triangle. So black triangle is silane in hydrogen, 20 millitorr. The open triangle is silane in nitrogen. So you have not changed the silane flow. What you have simply done is, instead of it being diluted in hydrogen, you have now diluted in nitrogen. Now nitrogen is inert, which means that it does not make a silicon N bond at the surface. So it does not have a passivating effect. So it has no impact on the open sites. So in nitrogen atmosphere, you have a lot more open sites than in hydrogen atmosphere, and because of this you see there is a sudden jump in the growth rates. That is significant. This is log scale. So, this is several times higher growth rate in that you get in nitrogen than in hydrogen. So, if you just want higher growth rates, consider doing a CVD under nitrogen. Now, why don't people ever do this, or why do at all people use hydrogen? Well, it turns out the slower growth rate has advantages. Remember, in the couple of slides before, we saw that very high growth rates tends to cause polycrystalline growth. So, that hydrogen is sort of useful in the way that it tempers the growth rate and allows for more epitaxial and high quality films to be formed. But if your goal just is growth rate, consider doing your silicon growth in nitrogen. Let us talk a few about some other issues such as hardware, doping, etc. to round up this lecture on CVD. So, this is what a typical equipment looks like. At this point, you probably expect something like this because we have seen the same thing in native oxide growth, we have seen the same thing in diffusion. So, there is a quartz chamber, the quartz chamber is heated. In this case, I am trying to show you probably an atmospheric pressure CVD. So, APCVD. So, APCVD does not necessarily have any pump because there is no pressure being created, the gases are just vented. You put in your precursors come from the left hand side, the precursor can be a liquid, for example, silicon tetrachloride is a liquid. And in this case, because this is a cold walled reactor, so you are doing RF heating. And there is a graphite susceptor which is what heats up, and because this is an APCVD reactor and boundary layer is a very big problem. So, you load the wafers at an angle such that you get uniform deposition everywhere. Compare this to this where this system which is probably an LPCVD system. So, you see a vacuum pump to pull the low pressure, you see a scrubber to scrub the exhaust that is coming. You have some gas sources, a very precise gas control and gas sequence. So, which gases to flow and when. This is a hot walled chamber, so you see a resistive heater, you see a susceptor, all the wafers are mounted axially because the flow to a first order does not affect things too much. All you really need to do is maintain temperature uniformity, and you can do that very well with this furnace, right. So, these are the typical versions of CVD equipment that you actually see. There is a general class of CVD which people call MOCVD, which is metal organic CVD. It is not a different type of CVD, it simply refers to the fact that the precursors can sometimes be metal organic. Till now we have discussed precursors such as silane, right. The problem with silane is a fairly dangerous gas. It is pyrophoric, which means it will catch fire if it is ever exposed to air. It is toxic in very small amounts. Nobody knows what silane smells like, because if you ever smelled it, you would not live to tell the tale. So, that is a problem because safety is a huge consideration in industrial manufacturing. So, people have always wanted these safer precursors, and one way you can make things slightly safer is by converting the silicon hydrogen bond into a silicon metal organic bond. For silicon, this is often not done, but very successfully done for other materials. For example, if you are trying to grow aluminum gallium arsenide, you might use TMA, which is tetramethyl aluminum. So, this is used in sort of say aluminum chloride, which tends to be very low vapor pressure or little hard to deal with. Okay, so in fact, in this case, maybe I misspoke in the sense that the reason for using TMA over AlCl3 is not safety, but vapor pressure. So, the advantage of metal organic precursors simply is that there is a much larger library. There are so many organic ligands out there. So, there are so many different types of materials you can make. A lot of them will have volatility. You can in fact tune the volatility. If you want higher volatility, you change the organic compound. If you want lower volatility, you put some other organic compound. So, there is a very large design space. It tends to make safer reagents, but it is a little arguable because TMA on its own is also a fairly bad material, but you can theoretically make some safer reagents. And typically it leads to very volatile byproducts, because the byproducts in this case tend to be organic, and organics tend to be volatile. I mean, alcohols, acetones, ketones, methane, ethane, they all tend to be very volatile. So, at very low temperatures they leave the surface. The disadvantage is it leads carbon contamination. It compared to hydrides, they tend to have lower vapor pressure, and they tend to be very expensive because you have to do a lot of chemical synthesis and purification to get it. The carbon contamination in silicon is not so much an issue because carbon is not a defect site. Carbon is very small molecule, so it's rarely a defect site in any material. But in very cutting edge requirements where carbon contamination also is an issue, you may have to rethink your use of metal organic CVD. The other word that you may hear is called plasma CVD. We will not go into more detail, just convey the fact that the CVD we have discussed till now, the energy for the chemical reaction was coming through thermal means. So, you are applying temperature and that was giving the energy for the reaction to occur. In plasma enhanced CVD, the energy comes from the plasma. So, we have seen the plasma before when we had talked about when you had talked about dry cleaning, right. So, when we had create a plasma and that plasma creates a certain amount of energy. Even in the introductory lecture, we had discussed dry etching and plasma and sputtering. So, in those cases, we also use plasma. So, that same plasma can actually be used to provide extra energy, and that allows you to do the deposition at much lower temperatures. So, plasma enhanced CVD is a thing. You can also do something very cool, which I personally find very interesting, is laser CVD. You can provide this laser through radiation, so in this case optical radiation. Not very useful for growing films on large substrates, but if you want to grow a wire, laser CVD is sometimes used. The growth rates can be fairly high. Finally, what is the quality of silicon that we actually get in modern epitaxy? The answer is extremely good. So, this is a figure that I think you have seen before in the introductory lecture, but here is your substrate. This is the epitaxial silicon you have grown, and by and large it is indistinguishable save for this one line that you see at the interface. If you zoom in, you actually see the perfect silicon lattice. If you look at its electron diffraction pattern, you again see the perfect silicon lattice. So, people know how to do silicon epitaxy fairly well and grow extremely high quality films. Couple of points on doping. Supposing you want to grow a dope film, the easiest thing to do is incorporate the dopant while you are doing the CVD. So, if you want to do phosphorus doping, you just introduce phosphine. If you want to do boron doping, you just introduce diborane. Often the doping level have to be very small. So, compared to the silicon atom density, the doping atom atomic density is much lower. So, the phosphine and the diborane must also be very low concentration. We get those very low concentrations by just making very dilute mixtures. So, instead of having 100% arsine or 100% phosphine, you have say 10 ppm of arsine or 10 ppm of phosphine and hydrogen. The rest of it is hydrogen. There are a few complications when you do that. The first complication is that the amount of doping you get is a function of the phosphine partial pressure. That is expected. The more phosphine you put in, the more doping you will get. But it often also depends upon details such as which material you are trying to deposit with. So, supposing your silicon is DCS, which is dichlorosilane or disilane, you would actually get different phosphorus dopings. The other complication is that often the dopant incorporation is not linear. So, at lower partial pressures it is 1:1, which is that for every additional phosphorus atom you will get additional doping, but at very high partial pressures the incorporation of phosphorus tends to become sublinear. So, for every one molecule of phosphorus you add, you tend to get like 20.25 phosphorus in actual doping. The concentration also depends upon what pressure you are doing. This has something to do with open sites. The full discussion a little more complicated, but it has something to do with open sites. With that hint, I'll leave it be. But at lower pressures, you tend to get lower concentration of dopants. At higher pressure, you tend to get higher concentrations. Also, the eventual concentration depends on solid solubility. CVD is a thermodynamic process. So, in general, you can't get higher doping than what the thermodynamic or the solid solubility limit. Finally, dopants sometimes have a catalytic effect. They sometimes might enhance the growth or deposition rate. So, here is an example where if you add diborane, the deposition rate of silicon itself, so the boron doped silicon grows faster than phosphorus or arsenic doped silicon. So, you have to be a little careful. Finally, a concept of auto doping. Auto doping simply refers to the fact that there is some unintentional doping in any reactor. So, this is what I am trying to show. Supposing you had a reactor and you had wafers and you had a susceptor and you are trying to grow your growth. But what if this wafer next to it actually has higher doping than this wafer? Well, the dopants might get from that wafer to the substrate. What if the backside of this wafer has some higher doping? Supposing you diffused a very high doped layer on the backside of this wafer. Well, that might also come out and go to the top. Maybe the person before you who did CVD did a very high doped run, and that meant the susceptor is now full of this high dopant, and that dopant will come from the susceptor and get onto your wafer. Or maybe the chamber walls are coated with a high level of dopant, and that might come to your substrate. So, there is a history here, and that history is complicated, and that history depends upon what somebody did before you, what the reactor has been used historically. So it's almost impossible to grow undoped layers in CVD. Virtually every CVD reactor will have some background doping, and that background doping is the process by which you get the background doping is called autodoping. Now there are details like hot walled cylinder and cold walled cylinders behave differently. Some reactors come with turbo pumps. You don't use a turbo pump during the growth. The turbo pump is simply so that it can suck out all the contamination before the growth starts. Some reactors come with HCl. That HCl is simply used to etch the chamber and the susceptor a little bit so that you clean up all the gunk or all the dopants away so that you have a virgin surface to start from. But even then, as I said, all reactors have some background doping. It really depends whether it's 10 power 14 or 10 power 16. Last slide on CVD, and that is selective epitaxial growth. So till now we had talked about CVD that was done on plain unpatterned silicon. In reality, you probably will have patterned silicon. So you will have portions that have silicon dioxide on them. So when you now do growth, now ideally you can either get a growth that is conformal, which is that you get growth both on silicon dioxide and silicon, but that is not good because silicon dioxide is not crystalline, right? So it will not seed the layer. So you will actually mess up this single crystalline growth that is happening from the silicon. The silicon dioxide growth will impede that growth that is coming from silicon. So what people prefer is a selective growth where the growth only happens where the exposed silicon is and happens nowhere else. So this is an example from one of the papers where there is oxide, there is no growth happening on the oxide, but there is a hole, and the hole only you get the epitaxy. This can be done by appropriate selection of precursors. Details I will not discuss, but simply what you are sort of doing is you are leveraging the desorption and the absorption rates on silicon dioxide versus silicon. Incorporation of chlorine or no chlorine, incorporation of etching and no etching, etc., to try to get selective growth. So I'll just say that this concept exists without explaining to you how it's done. We have done all silicon CVD, one slide on other materials that you can do with CVD, for example, silicon oxide. So you can, for example, for silane and oxygen to get silicon dioxide. Another very popular material is TIOS, which is siloxane. So it has a silicon oxygen bond. You heat it up, the silicon oxygen bond breaks, and you form an SiO2 layer. So these kind of things can also be done. Details can be looked at from this link. So with that, we come to the end of the CVD. In this module, we sort of understood what is CVD. We talked about how what the precursor is, how the vapors are transported. We discussed a little bit of the viscous flow regime and how you design the flow in a reactor, and how the Reynolds number of the reactor will tell you a lot about what the boundary layer is, and whether the presence and absence of the boundary layer will tell you whether the flow deposition will be uniform or not, etc. Then we took two special cases of AP-CVD reactors and LP-CVD reactors and discussed details, hot walled, cold walled, discussed details. We discussed something about nucleation. We discussed something about how there is a competition between nucleation and growth and how that leads to epitaxy or polycrystalline growth. And we then looked at some equipment details and some special cases such as doping, selective growth, and silicon dioxide CVD. So with that, we come to an end. And the next lecture, we'll talk about atomic layer deposition.